So let's look at sort of more complicated forms of differentiation. Now, when we derive e to the power of x, we know that we get e to the power of x. Now, that's just a special. That's basically what makes e a special value. It has this special place in calculus. It's this special value that has that function. Where e to the power of x derived equals e to the power of x. Now, that doesn't mean e to the power of, let's say, ax plus 1 is equal to derived, sorry. So let's say fx equals this. Now, the derived version of fx does not equal to ax plus 1. It does equal to basically the differential of what's up here multiplied by this. So let's say we have, and I'm just doing a quick, I think you've probably all seen this before, but if we have fx equals to ex squared, then the differential is equal to 2x times ex squared. So that's the differential of what's up here getting multiplied down to there. And that's our system. Should be equals. So that's a pretty simple system of deriving. There's a pretty simple formula that you use a process for this specific type of value, which is e, this magical value that exists in calculus. Now, how do you integrate? Well, integration is pretty similar. So if you integrate e to the power of x, then you will just get e to the power of x plus c. And that's because if you derive e to the power of x, it'll be the derivative of x, which is just 1, multiplied by e to the power of x. So it'll be e to the power of x. On the other hand, you often will have much more complicated situations. So this is the best general formula to look down at to look at here, because it covers everything. These only encompass certain forms. For example, this only encompasses the form where what's up here is a linear function. This covers any type of function. So if you ever see the differential of a function multiplied by e, which has the function as its power, that means if you derive this, it'll just be equal to e with the function to its power, and then of course plus c, as typical. And that can obviously be applied here to this linear one, because we have, in this scenario, let's say we had e to the power of ax plus b. Then if we derive that, it would be equal to e to the power of ax plus b plus c at the very end. And that's because we're in this form here. This derived only has a, so a goes out the front when we derive it. So then when we antiderive it, we would get rid of the a. We'd do the inverse process. In this scenario, we don't have the a out the front, so instead we have the 1 over a there, because we assumed that when we derived, if we did derive this, the a would go out the front, and then it would be a over a, and it would all cancel. So basically, understanding these formulas, understanding why they are sort of how they are, is I think the best way to do it, because there's lots of different formulas, but if you understand the basic logic, and the easiest to look at is this formula here for that, then this encompasses all of those different forms. And even if these other forms, if knowing them does allow you to do your working a lot quicker, and they are very useful, understanding the most basic formula is definitely the most versatile. Understanding these ones is more so useful for doing work quickly in an exam, basically. So now we're going to look at logarithmic integration without actually doing any examples here, which maybe at the end, if we do have some time, we can go back and create and generate some examples for this. So